Recording. Yes, it's recording. Good evening, all of you. Myself, Harish Kannadi. I'm the PMRF fellow at Department of Hydro and Renewable Energy, IIT Roorkee. I'm the PMRF NPTEL-TA for the Basic Electrical Circuit course, and this is the today we are going to discuss about the assignment 12 problems. We will quickly look into the problems, and the first question is for the system governed by the set of equations, means a system is modeled with a set of equations. Okay, it's having the input of u of s, sorry, it's a time u of t, and having an output y of t. Okay, the system is represented in following equations. Is represented with the three equations. We have to find out the transfer function of the system, that is y of s by u of s. It means these equations are in time domain. We have to convert into s domain by applying the Laplace transformation, and we have to find out the transfer function of this system. Okay. First, let us consider this one is equation 1, this one is equation 2, and this equation 3. By applying the Laplace transformation for the equation 1, can we write it is a x1 dx1 by dt. We can write s into x1 of s equal to 2. It's a x1 Laplace transform x1 is x1 of s plus Laplace transformation of x2 is x2 of s plus Laplace transformation of u is u of s. This is the Laplace transformation of equation 1. However, when you consider equation 2, what's the Laplace transformation of dx2 by dt? It is simply x into x2 of s equal to minus 2 into x1 Laplace transformation is x1 of s, and u Laplace transformation is u of s. Okay. And what's the third equation? Laplace transformation of third equation is y of s equal to 3 into x1 of s. We have the following three equations. However, we want the equation by y of s by u of s. There is no direct relation between y of s and u of s. Y of s in equation 3 and u of s in these two equations. So we cannot relate these two equations. However, y of s is related with the x1 of s and u of s is related with the x1 of s. So we can use these two equations and we will find out that u of s, and in terms of we will find out the x1 of s in terms of u of s, and we are going to substitute in this thing. Okay, take the equation 2. Sorry, here. Okay, what is the equation 2? Equation 2 equal to s x2 of s equal to minus 2 x1 of s plus u of s. Okay, here we can represent x2 of s, so the s will be goes that side. It is minus 2 x1 of s plus u of s by s. We can write like this, whereas we will put this equation, let us suppose we number this equation 4 in equation 1 in place of x2 of s. So the equation 1 will become s into x1 of s into x1 of s equal to 2x2, right? 2x1 of s 2 x1 of s plus x2 of s. Instead of x2 of s, we are putting this function instead of x2 of s. That is, yeah, I will represent with some different color. It will be good. Yeah, it is minus 2 x1 of s plus u of s by s. Instead of x2 of s, we substituted the equation 4 and plus u of s. Okay, this s you can multiply both the sides in terms of s, so that will the equation will be becomes like if you multiply both sides with s, you can multiply in both the sides, so the equation will becomes like s square x1 of s. Why? Because s into s it's x square, so it is 2s x1 of s. This s and s will be cancelled. It will be minus 2 x1 of s plus u of s. Here there is no function. It is simply s into u of s. Okay. The whole function, the equation, these are two variables. One is x1 of s and u of s. Okay. However, we have a equation 3. Equation 3 it is related with y of s and x1 of s. So we can represent x1 of s in terms of u of s, and we are going to substitute in this. So we can write s square x1 of s. Um, this side it will be plus 2s x1 of s. If you bring from this side, it will be minus 2s x1 of s. It will be minus 2s x1 of s. Okay, here it will be minus 2 x1 of s. If you bring it to that side, it will be plus 2 x1 of s. So plus 2 x1 of s equal to, here you can common u of yeah, what is there, u of s plus s into u of s. Okay, from this equation you can common x1 of s. So x1 of s equal to s square minus 2s plus 2. uh, from the right hand side equation you can common u of s. It will be 1 plus s. Now you can write x1 of s equal to 1 plus s by s square minus 2s plus 2 into u of s. We can write like this. We just bring this equation into this numerator, sorry, denominator. So it is numerator is 1 plus s and denominator is s square minus 2s plus 2 into u of s. Let me add one paper. Yeah. So we got the equation x1 of s in terms of u of s. We can classify from the equation 3 and equation 5. We can write y of s, right? How can we write y of s? Y of s equal to 3 into x1 of s. That's what we here, no? Y of s equal to 3 into x1 of s. So the equation will become 3 into, instead of x1 of x, we are substituting the equation 5. It will be 1 plus s by s square minus 2s plus 2 into u of s. Okay, one can bring this u of s into this denominator function, so the equation will becomes like y of s by u of s equal to 3 into 1 plus s by s square minus 2s plus 2. Okay, this is what the function we need. It is a transfer function of the system y of s by u of s, Laplace transformation of output by Laplace transformation of input. Just we calculated from these three equations. The answer will be 3 into s plus 1 by s square minus 2s plus 2. That's option A. I hope this is clear. Actually, the whole system is represented in the following equations. So we want Laplace transformation of output, that is y of s, by Laplace transformation of input, that is u of s. So there is no direct equations related to y of s and u of s. That's why we use these three equations and we are represented y of s and u of s from these three equations, and we calculated y of s by u of s. So this is the transfer function of the whole system. I hope this question is clear. We are moving to the next question. The next question is, yeah, under mechanical rotational systems and electrical system, the quantities that are not analogous are. It means under the mechanical rotational systems, we can quickly draw the mechanical rotational system. Yeah. This is a mechanical rotational system. The mechanical rotational system is having the constants of this friction constant, it is B. Let us suppose the spring constant is K, and weight of the unit we can consider J, inertia, so torque, and angular velocity omega, and angular displacement theta. Okay, from the D'Alembert's theorem we can write the total torque produced, that is T, equal to, we can write this J d omega by dt plus b into omega plus k into omega into dt. All right, and one more thing, we can write omega equal to, that is angular velocity equal to this just change in displacement, angular displacement, that is d theta by dt. This is the mechanical rotational system. First we written the equations for the mechanical rotational system, and we need to write the electrical systems which are analogous. In electrical, we can represent the same in two terms, in two ways. First, we will represent in simple voltage, you can consider series RLC network. It's R, L, and the capacitance of C. So here the input is, let us suppose V of t, and this R. So the voltage drop across the resistance is, it is VR, it is L, the voltage drop is VL, and it is C, the voltage drop is VC. Okay, it is a simple series RLC network. We can write the equation from the KVL equation. What is the KVL equation here? Here we can write V of t equal to, let us consider the current in this particular loop is I of t. So V of t equal to VR. It is a simple KVL equation, VR plus VL plus VC, right? The current through the resistors is I of t. So what is the voltage drop? It is, from the Ohm's law, it is R into I of t. Okay. And coming to the current through the inductor is I of t. What is the voltage across this inductor? It is VL equal to L into di of t by dt. L into di of t by dt. Similarly, the I of t of the current is flowing through the capacitor. The voltage across the capacitor is Vc of t. One can write the Vc of t equal to 1 by C integral of I of t into dt. Right? This is the one way of representation. Okay. If you consider a parallel network, a parallel RLC network, we will use some different color. Okay, so resistance R, inductance and capacitance. Here it is I of t, and here it is like IR and IL, and this is IC. Okay, we can apply a KCL at this particular node. What is the KCL equation? The KCL equation simply it is sum of the currents, right? I of t equal to this is entering current, I of t equal to leaving currents, that is IR plus IL plus IC, right? We will consider this node is having a voltage of V of t. These all are connected in parallel. So the voltage across the resistance and inductance and the capacitance is same, that is V of t. So how can we write this IR? From just simple Ohm's law, IR equal to simply voltage across the resistor by resistance, that is V by R, correct? And what about the inductor? Current through the inductor? The current through the inductor is 1 by L integral of V of t into dt. What about the current through the capacitor? I equal to C into dV of t by dt. Okay, here we can represent the rotational system in terms of series series RLC network or parallel RLC network. So we can relate those two. Because yeah, we can draw one more. Okay, we are comparing these two. First one, we will compare this equation and this equation. So in place of t, that is torque is equivalent to voltage there, right? Why? Because here it is torque, here it is voltage. So the torque equal to voltage, and it is j d omega by dt, j d omega by dt. So here only the differentiation derivative term is this one, that is L di by dt. So we can equate the inertia with inductance. And next one, here it is b into omega, here it is r into I of t. So we can represent this equivalent of b equal to r. So the b equal to r. Coming to the last term, it is a integration term. It is multiplied with k integral function. Here we are having the integration term. However, our multiplication factor is 1 by c. So the k equal to 1 by c. And here we represent all the equations with omega, the angular display, angular velocity. There it is I of t. And what is the omega? Omega equal to, it is a angular velocity. It is change in the angular displacement, right? That is d theta of t by dt equal to I of t. We can write I of t in terms of charge, that is dq of t by dt, just from the above equation only. We are representing just from the this equation only. So we can rewrite this thing, that is theta of t is same as q of t. Okay, the response is, it is, this response is known as torque voltage analogy. I hope this is clear. We are comparing now this equation, this equation with this equation. So in place of torque, earlier it is equivalent to voltage, now it is equivalent to current. That J is the inertia, it is having a differentiative term, that is derivative term. Here we are having a derivative term with C. So the inertia we can represent with C. And coming to the resistance is same as 1 by R, it is conductance. And what else? Yeah, up to B we reach, and integrated term, it is K, K equal to 1 by L. And earlier it is angular velocity, here it is voltage V of t. And we can represent angular velocity in the same as previous one, it is d theta of t by dt, it is angular displacement. And v of t we can write in terms of flux, that is d phi of t by dt. So the theta of t is analogous to the phi of t in torque current analogy. This analogy is known as torque current analogy. However, this analogy is known as torque voltage analogy and torque current analogy. So the question is, under the mechanical rotational system and electrical system, the quantities that are not analogous. So analog velocity and the current, angular velocity and the current. Here, angular velocity, that omega, and current is analogous to each other. So the answer one is correct. These two are analogous only. And angular displacement and charge. So the angular displacement, that is theta of t, sorry, angular displacement theta of t is analogous to the q of t, that is charge. So this one is also correct. Viscous friction and coefficient of resistance. The viscous friction, that is uh, friction coefficient, that is beta b, and resistance r are analogous to each other. So this one is also correct one. And moment of inertia means it is j, right? And conductance is 1 by r. So we can see that in the both the aspects, in the first torque voltage analogy, moment of inertia is equal, analogous to inductance. And second torque current analogy, the moment of inertia is analogous to capacitance. So the last one is not analogous. So this is our answer, it is not analogous. So we can erase sorry. Now the answer is this one, the moment of inertia and the conductance are not analogous to each other. I hope this question is clear, right? Which are the terms are not analogous to each other? So for that thing, first we represented the rotational system and the corresponding equations. And to torque voltage analogy, we represented with a series RLC network, and from those things we are represented the equations. And coming to the torque current analogy, we represented the corresponding equations, and we identify the analogous terms, torque voltage analogy and torque current analogy. From there, yeah. Coming to the next question, Consider the reciprocal of the capacitance and torsional spring stiffness as analogous quantities. The system is considered as. Okay. Uh, Consider the reciprocal of the capacitance. Reciprocal of the capacitance means it is 1 by C. Okay. And spring coefficient K, which are analogous quantities in each other. We already have the torque voltage and torque current characteristics, torque voltage and torque current here. So we can compare here. Here, this from this we can say that the K equal to analogous to reciprocal of the capacitance. So we can directly say it is a torque voltage analogy. I hope this question is clear. First, the question is consider the reciprocal of the capacitance. The reciprocal of the capacitance means 1 by C and spring stiffness, that is K, as analogous quantities. The system is considered as, it means these two are analogous to each other. So we already have that rotational equation. So we are comparing these equations here. The spring coefficient K is analogous to the 1 by C, that is reciprocal of the capacitance. So it is the torque voltage analogy. So the option A is the correct one. We're moving to the next question. The next question is the relationship between the force F of t and the displacement x of t of a spring mass system with a mass m, viscous damping d, and spring constant k is, there is a equation that is given as m d square x of t. This equation I am reading: m d square x of t plus d dx of t by dt plus k x of t equal to f of t. It is the equation, the second order equation in the time domain, which is having a constants of m, d, and k. Okay. X of s and f of s are the Laplace transformation of x of t and f of t. All right. And with m equal to, the constant values are given here, that m equal to 0.1 and d equal to 2 and k equal to 10. In appropriate units, we need to find out the transfer function, that is x of s by f of s. Okay, I'm rewriting the same equation: m d square x of t by dt square plus d into dx of t by dt plus k into x of t equal to f of t. This is the given equation of the system. So we can substitute the values of m, d, and k in the equation. The value of the m is, it is 0.1, 0.1 d square x of t by dt square plus d into dx of t by dt. The value of d is 2, 2 into, yeah, we can, yeah, 2 into dx of t by dt plus k into x of t. The value of k is here 10, 10 into x of t equal to f of t. Okay. Now we are having the equation in the time domain. So we need to find out the transfer function. So we are converting this time domain equation into the S domain equation by applying the Laplace transformation. So we are converting into S domain equation by applying Laplace transformation on both the sides. Okay. Give me a second. Yeah. So we are applying Laplace transformation on both the sides, right? Now initially it is a constant, it is 0.1. What is the Laplace transformation of d square x of t by dt square? It is a second order differentiation equation. So the Laplace transformation of second order differentiation is s square, and the Laplace transformation of x of t is x of s, right? Plus 2 is the constant, and Laplace transformation of d by dt is s, and the Laplace transformation of x of t equal to x of s, right? And 10 into x of t Laplace transformation of is x of s, and the f of t Laplace transformation is f of s. Okay, here in this equation there is x of s is we are having x of s in the all the terms. We can make x of s common, so the equation will becomes like we can take x of s common. It is 0.1 s square plus 2s plus 10 equal to f of s. What is the transfer function we needed? We need f of x of s by f of s. So we can write this x of s by f of s. We can bring this f of s to denominator side f of s. So we can put this to denominator function is this one and some constant k. So the equation will becomes this is 1 by 0.1 s square plus 2s plus 10, right? There is a fraction of 0.1. To eliminate this thing, we are going to multiply with the 10 on numerator and denominator. So the numerator function will becomes 1 into 10, it is 10, and 0.1 into 10, it is 1, it is s square, and 2 into 10, it is 20s, and 10 into 10, it is 100. That is x of s by f of s. So the transfer function equal to 10 s square, 10 by s square plus 20s plus 100. That is 10 by s square plus 20s plus 100. Option 1. Alright. Just they given the equation in the time domain. So we are having these constant values of m, d, and k. We substituted the constant values and we applied the Laplace transformation to the equation. From the Laplace transformation, we simplified that equation and find out that the transfer function x of s by f of s equal to 10 by s square plus 20s plus 100. Okay, all right. Uh, what's the fifth one and the problem? It's the last problem, I hopefully. Uh, yeah, force balancing equation of mass element is there's an element of having mass m. Okay, it's having the displacement of x of t, and it's having the velocity of u of t. Okay, how can we write this force equation? The force equation equal to F equal to sorry m d u of t by dt, what we seen in the previous. And coming to this, u of t is the, here it is u of t is the velocity. We can represent the velocity in terms of displacement. That is, the velocity equal to change in the displacement is d into x of t by dt. Okay, we can substitute this equation in this. So the force will be F equal to m d by dt of x of t. We can represent this in F equal to m d square by dt square into x of t. Right, at F equal to m d square by dt square into x of t, that is m d square x by dt square, the option A. Yeah, thank you very much. Thank you for being. Yeah, I think we can end the call for everyone. Stop recording.